All right, so we're going to talk about 9.4 to 9.6. I am very sorry that this video is late, everybody. 2 minutes late. So this time your reading guide, I would recommend reading it. I always recommend reading it, but the thing is, with this one, there's actually one section that you really need some guidance through 9.5 because the book, I don't think, actually explains it correctly anymore because of some new research. So basically, let's talk about 9.4 quickly, covalent bonding and orbital overlap. There's two major ideas here that I want to focus on. One is the idea with these orbitals is that when two things bond, their orbitals overlap with one another. Now, you need to understand this is the bonding theory that you have learned so far. This comes from valence shell electron pair repulsion and Lewis structures and all of that. Okay, this is that bonding theory. So we're going to learn a different one at the end of this unit. That's probably a little more correct than this. Okay, there are just some problems with this theory that that can't really be solved unless you have a different way of looking at it. Okay, so but the idea here is these things, these atoms, approach one another, right? And as they do, the reason they would form a covalent bond is because you get the electrons from one of the electron clouds attracted to the nucleus of the other one. Okay, and so then they're going to move closer to one another. All right, now, here is the graph that's going to clear up all confusion from that test or that quiz question the other day. And I forgot we hadn't done this yet, okay? There is a perfect distance of two atoms from one another when they form a covalent bond where they have the lowest possible potential energy. This is potential energy here, okay? And so that point is actually where they usually hang out when they're bonded together, okay? If they move any further apart from one another than that, the potential energy increases, okay? So they're getting further apart. If they get too close together, then the nuclei start to repel one another, and that potential energy really jumps, okay? Now, why are we saying there's more potential energy if it's in a less stable state? This is the important thing that you need to understand here, and if you haven't taken physics, it's a little tricky. I'm telling you, if it's in a less stable arrangement, it has more potential energy. Does that make sense to you when I say that? I mean, we can think about it with all sorts of... gravitational is really the best way to think about this, right? If something's in not a very stable state gravitationally, in other words, like this, you can't see this on the video, but this pencil that's on the very edge of my desk, that's not very stable. That's a high amount of potential energy, right? Because all it has to happen is just a little bump here, you know, like a really little bump. There you go. And it falls, right? Now it has a lower potential energy. It's in a more stable state because it's not going anywhere now that it's on the floor. Does that make sense? Okay? You got to think about atoms really in the exact same way, okay? The more stable the bond, the lower the potential energy, okay? But also the more stable the bond, the more energy it takes to break it. Does that make sense? Okay? So the question I think I asked in the quiz was, we had a single bond and a double bond. And the question was, which one of those contains the least potential energy? Okay, which one of those has the least potential energy? Well, the answer to that question would be the one that's the most stable. Does that make sense? Okay? This carbon-carbon double bond is a little more stable because the electron density in the center actually draws the atoms a little bit closer to one another. There's more attraction because you've got more electrons here attracted to each of the two nuclei. That's a more stable arrangement. Because it's more stable, there's less potential energy there. Okay? Does that help kind of clear that up? I wasn't doing a great job of explaining that the other day, and then I realized we hadn't talked about this, and that's why it wasn't making a lot of sense to you guys. Okay?
Mr. Waters, contact the main office, please.
All right, so hopefully that clears that up. So that's the bonding thing from That's really what you need to know from 9.4, okay? It's just the idea of how those covalent bonds happen, why they happen. Two things are going to bond covalently if they can enter into a more stable arrangement than they had when they were just by themselves, okay? So that potential energy you would expect, as the bond forms, the potential energy lowers. Now, that also corresponds to what I've told you about what happens when a bond forms, okay? If a bond forms, then there's a decrease in potential energy in the system. If the energy of the system decreases, what happens to the surroundings? Say that again, okay? So these two things come together, they form a bond, okay? Their potential energy decreases. So the energy of the system decreases. So then what happens to the energy of the surroundings? Increases. Okay, remember what I said. Bond formation is exothermic. Releases energy, okay? Bond breaking is endothermic. You have to put energy into it to break the bond, okay? I think this is one of the hardest concepts in AP chemistry. It's just, where's the energy? Where is it going? How is it working? Okay, but does that make sense? Okay, so you got to kind of think about it like that. All right, so moving on. Yeah, I don't know that we need to talk about that question right now. See, what I ended up doing is kind of going back through my notes a little bit from a couple of years ago because they've got the good pictures in there, okay? So here's where the book doesn't quite teach the truth, all right? So this is where you have to be careful. Now, if you look at your reading guide that I gave you for today, if you look at the additional questions related to the reading, number 7 here, it says, for section 9.5, simply read my explanation here. Don't worry about reading out of the book, okay? Now, the unfortunate thing is there's pictures in the book, right? But this whole hybridization thing, they have made it very clear on the AP exam that you don't really need to understand the hybridization thing. And part of that is they're not really sure how much of this is even correct anymore, okay? It seems like it's almost universal now among chemists that the d orbital hybridization just does not occur. So I don't know if you guys remember learning this last year when you talked about the sp3d2 and sp3d hybridization. Basically what they say now is, nope, that really doesn't happen. We don't think that happens. These d orbitals are not involved in hybridization. Okay, now s's and p's might still hybridize, possibly, or there may be another explanation out there. Okay, but for now, what the AP exam has said is, all we need you to know is the hybridization up to sp3. Okay, because we're pretty sure that sp3d and sp3d2 do not happen anymore. Not that they don't happen anymore, not like they ever did, but we're pretty sure now that those don't happen. Okay. So here's the basic idea with hybridization. I don't know if this will jog your memory a little bit. But the idea with hybridization is, in order for something to bond with something else, orbitals have to overlap, okay? And so what you end up with here, if you want beryllium to bond with anything, it doesn't have any available open orbitals right now, okay? So the theory goes, the beryllium would promote an electron into here. So now it's got one electron in a 2s orbital, one electron in a 2p orbital, and those end up hybridizing with one another, forming this sp blend, okay? And then you end up with something that looks kind of like this right here, okay? These are the hybridized sp orbitals. Now again, does any of this really happen? I don't know, okay? But this is really, and I try to explain this here in number 7, okay? It says quantum theory says CH4 should not be symmetrical because you've got your s and your p orbitals, all right? So this is a way, what we really observe in real life is that CH4 is symmetrical, all right? So there's got to be something going on there And one of the best ideas is hybridization. Okay, these s and p orbitals are hybridizing, so you end up with, instead of an s orbital and 3 p orbitals, which would make this thing lopsided, it would make it non-symmetrical. Okay, what you end up with instead is 4 identical orbitals that can all bond in exactly the same way, and you end up with a CH4. Okay, so this is an example of BeF2 with those hybrid orbitals. Then there's an example here with, what is this one? For boron, BF3, I think, maybe. So you're going to end up with a trigonal planar because you've got these 3 hybrid orbitals here. Okay. And then with carbon, when you do something like CH4, then you're going to end up with something like this because you end up with 4 identical sp3, I guess 4 identical sp orbitals. Okay. No, I guess it's sp3. So that's kind of the idea with hybridization. Okay. I used to teach that a lot more than I do now because as the years have gone on, it's kind of been more and more like we don't really even know if this is right. So, I mean, it's useful to talk about this because this is one of the better models we have for bonding right now. And all a model is, when you get down to the atomic level, it's scientists kind of flailing in the dark trying to figure out what's the best explanation for the data that we have. Okay, and that's kind of what this is. All right? It kind of is. Yeah, it's kind of like a guessing game. But at the same time, and these are good guesses, right? Because it's based on all this data. If it doesn't explain the data, then it doesn't get to be a guess. All right? So anyway, that's kind of the idea on that. I was referring you to figure 9 point. Okay, so now we're into multiple bonds. Okay, and this is where you do actually need to understand this. So the hybridization stuff, you can kind of forget about that. 2 ways orbitals can overlap to form bonds. One is a sigma bond and one is a pi bond. Now this you do need to know. All right, remember that from last year, sigma and pi bonding. So sigma bonds, that's direct overlap, okay? This is an example of a sigma bond right here. This is an example of a sigma bond. This is an example of a sigma bond. So when you have that direct end-to-end overlap between 2 things, okay? Pi bonding is more like this, okay? So you've got the 2 parallel p orbitals. Pi bonding can't happen with s orbitals, by the way. It can only happen with p's, okay? Because those are the only ones that would ever be parallel to one another. So you end up with these 2 areas right here are your sigma bond. It's the areas of overlap between 2 parallel orbitals. Okay? So you need to know the difference between an s and a p bond. Okay? Sorry, sigma and a pi bond. I didn't mean to say that. It gets really confusing. You've got the s and the p orbitals, and then you've got sigma and pi. And it seems like those should be related to each other somehow, but they're really not, because you can have sigma bonding in 2 pi orbitals. Dang it. Sigma bonding in 2 p orbitals, sorry. Or you can have, pi bonding in p orbitals. You can only have sigma bonding in s orbitals, okay? But just because sigma starts with an s and pi starts with a p doesn't mean that they're related to the s and p orbitals necessarily, okay? Sorry. All right, so when we have a single bond, that's always a sigma bond, okay? Sigma bonds always form first. You remember talking about that last year? Sigma bonds are always the first bond to form, okay? So if you have a single bond only, you know that's 1 sigma bond, okay? If you have a double bond, then you've got 1 sigma, 1 pi, all right? And then if you have a triple bond, you've got 1 sigma bond and 2 pi bonds. And I'm going to show you, I've got a picture on here of how that works in case you need a refresher on that. So the way this works, I'm sorry, I know I'm moving fast, but I'm trying to get done with this in about 20 minutes like normal. You remember this picture? I think I showed this to you last year as well. Okay, nice and confusing. But what you've got here, essentially, you see the end-to-end overlaps that you've got here, here, and here. Okay, everybody see that? So these are sigma bonds right here because you've got a carbon and a hydrogen orbital overlapping, right? So that's a sigma. This is a sigma down here, because that's a carbon-hydrogen overlapping. You've got lone pairs over here, all right? So that's not sigma or pi bonds. That's just lone pairs. This bond in the middle between the carbon and the oxygen, this first bond that forms right here is a sigma bond, which they already noted that. I guess they wrote a sigma here and here too. I didn't see that. But the pi bond, the second bond that forms when you have this double bond right here, is going to be this and this right here. That's one pi bond, because if you look at this, erase all of this that I just did. These were originally p orbitals right here. Okay, can you see that? And they ended up, because they're parallel, they end up overlapping, so the electrons can kind of travel anywhere in this region. Okay? So that's the difference between a sigma and a pi bond. Okay? What you essentially need to know how to do with this for the AP exam, you need to be able to look at something like this, just a Lewis structure, and you need to be able to say how many sigma and how many pi bonds are there in this structure. Okay? Which that's easy, right? Because this is a sigma, this is a sigma. There's one sigma in here, and then the other one's a pi. And that's it. Okay? 3 sigma, 1 pi. Pretty simple. Now, the other nice thing that, does it talk about resonance here? I'm trying to remember. Yeah, here we go. Okay. So resonance, you can actually talk about resonance in this way as well, and I'm not sure that we did this last year, but I do want to talk about this a little bit, okay? So when you draw a resonance structure, for example, for NO3 minus, okay, you would draw something that looks like this, all 3 structures here, okay? But remember, what we talked about before, in reality, this is more like a 1 1/3 bond on each of these. You kind of take the average of it, okay? So what they think is really happening here is something that looks a little bit more like this, okay? Do you see the difference there? So what you have here is all of these p orbitals that are all parallel to one another. And you end up being able to have overlap between all of them. So these electrons become delocalized. You've got this extra pair of electrons that can kind of go anywhere in these parallel p orbitals. And that's why you end up with a 1 1/3 bond, okay? So if you were talking about the bond strength on NO3, and you've got your Lewis structure that you've drawn for that. Whoops, too far. You've got your Lewis structures right here. Then really, this ends up being a little bit stronger than a single bond, but quite a bit weaker than a double bond overall. It's kind of a 1 1/3 bond. Okay, it's also a little bit shorter than a single bond, but it's quite a bit longer than a double bond. Okay, and the reason for that is because of that extra pair of electrons that you've got floating around. Not floating, I don't know what electrons do, who knows. Doing whatever they're doing inside these parallel p orbitals, that's strengthening those attractions just a little bit between the nitrogen and the oxygen atoms. Does that kind of make sense? Yeah? Hopefully that makes sense. But that helps explain resonance just a little bit better, I think. Because I want to make sure you have a good understanding of resonance, because they can ask you a question about that. Okay, so when they're talking about delocalized electrons, this is what they're talking about. This structure down at the bottom here. Okay, that's kind of the idea. This same thing can happen in like a benzene ring. This is why benzene is so stable, because it basically has alternating double bonds here, but again, that's not really what's happening, because this is a resonance right here, okay? What's really happening is something more like this, okay? You've got all these overlapping p orbitals, and those 3 extra sets of electrons are just delocalized in here, and they help stabilize the entire structure. Okay, so a benzene ring is a very stable arrangement for that reason, okay? All right, I think that's pretty much all we need to talk about with The resonance, yeah, and then we get into molecular orbital theory, and that'll be fun. But we'll do that tomorrow. Okay? Any questions on any of that stuff? Again, most of this we talked about last year. If you look at number 16 on here, on the reading guide, this basically explains what you need to know. Okay? 2 domains around the central atom, that's sp hybridization. 3 domains, sp2. 4 domains, sp3. Okay? If you remember that about hybridization, and you remember how to pick out the number of sigma and pi bonds in something, then you're probably just fine. And then there's a couple other things, a couple other pictures that I put on there about carbon nanotubes and graphite and how that works. I thought that was kind of interesting. So you might look into that because they're probably going to put some of that kind of stuff on the AP exam this year as well. All right? We'll probably talk about that a little bit more in class tomorrow. Okay? That's it.